To become experts in manufacturing, we need to master both the quantitative and qualitative aspects of each process. By quantitative aspects, I mean things like the scaling laws and physical process parameters that we derived a few minutes ago. By qualitative aspects, I mean the relationships between those process parameters and part quality, which we could relate to those process physics, but involve a lot of other expert understanding of the process and the complex interactions between the process variables. Things that you can't always write equations for, and for which you need that really in-the-shop understanding from making parts and looking at parts. And we're going to do that in this section, and that's why it's called defects in the process window. So for injection molding, we're going to define the process window as connecting, in this two-dimensional space, temperature and pressure. And we know that temperature and pressure are two important process parameters that we can generally control in the process. And the window, as we'll call it, is the gray area here, region between low temperature and high temperature and low pressure and high pressure, which for the moment we'll say we must be inside in order to make good quality parts. And around the periphery here, we have some labels. And the labels include important types of defects that we're going to define by looking at parts in a moment. At the bottom left, we have what's called a short shot, and that's when plastic doesn't fully fill the mold, and that can be by either not injecting enough plastic, or, if we think back to the fundamentals of polymer softening and flow, when the temperature is too low or the pressure is too low, and therefore we can't force the plastic all the way in, no matter how hard we're able to try. At the up end, along the top, we have thermal degradation. If the temperature is too high, the polymer is, of course, going to break down, and that will degrade the quality of the part. At the far right, we have a defect called flash, and that's when the pressure is too high, and therefore we're forcing plastic not only all the way into the mold, but out the parting line, creating an additional piece of solidified plastic that's a defect that we want to get rid of. And then generally along the low temperature side, we have the issue of having to melt the plastic, so it's not really a defect part-wise, but it means that you haven't melted the plastic and therefore it can't fill the mold completely in the first place. So now let's see some examples of these different kinds of defects. And here we see a good example of a short shot. So this short shot was created by some of our students on campus at MIT, and while making their yo-yo, which we've seen before at the right, the Ironman arc reactor yo-yo, they made a series of parts, each with a different shot size setting on the machine. And that means that they specified how much plastic was going to go into the mold, and they started out by specifying not enough. So the first piece on the left, the plastic fills their mold cavity by almost half. And all the way to the far right, they fill it with enough plastic, and therefore the part completely fills the mold cavity. We see the molds down here, and if I go to the camera, we have the yo-yo once again. And with their test parts, they were making a black color version of the eventual blue piece that fit nicely inside their outer ring. And by placing the part inside their cavity mold, we can really get a picture of how the plastic flowed. We have the injection point here and the runner leading to the gating point of the part on the side. And you can imagine the plastic flowing circumferentially through the mold cavity and along the bottom. And here their shot size, the amount of plastic they injected, was only enough to fill the mold this far. And over here I have their almost completely filled part with a little bit of a short shot on the far side here, and then the completely filled component that was then transferred to the blue color and for which the parameters were adjusted to make the final components of the yo-yo. Now here's an example of flash, and as I said, flash is the defect where you force the plastic too hard across the mold and you generate this unintended extra feature which hangs off the side. And we see the same part here. This is another yo-yo part. Plastic is injected from this side, flows around the periphery, and flash exists here because the pressure is too high or because the mold halves that open and close like so aren't precisely machined or aligned such that the plastic cannot flow into the gap defined by the parting line. And we need a parting line so you can take the molds apart cleanly in two halves, but the parting line can't be too big or cannot be non-uniform such that flash is generated. And therefore the process parameters or molds would have to be edited to remove the flash, or if you can't get rid of the flash, you have to take it off after the process. And you might also have come across parts that have flash on them, and parts that you buy with flash, and that's, for example, a low-cost clothing hanger, and there, there's really no driving force to make the part better quality. If they can make it cheap and functional, in some cases that's good enough. Now here we see an example of burning or thermal degradation, and this is a part of another yo-yo from our class, and the burning occurs over here at the far side. And this is a special case where the setting for the machine, the temperature of the mold and the plastic was fine. It was the right melt temperature, but air was trapped in the mold, and the air pocket happened all the way at the opposite side of injection where the plastic will last reach, and the air got so hot that it led to local burning of the plastic. And here on the camera is the same part. Here's the location of burning, and what the students did is they machined a small channel in their mold such that the air could escape and therefore burning didn't occur, but the channel was so small such that the plastic didn't flow out along that channel and create an instance of flash. And I also want to point out what's called a weld line. Because the plastic is injected over here, it flows circumferentially around, and some cases, especially in certain colors, you see a weld line that represents where the plastic meets. And that, in some cases, is a defect that you want to tune the process parameters to help eliminate if your visual appearance is important as well. So to summarize our process window, we see the defective parts that we examined placed in the appropriate general ranges of the temperature pressure map. And earlier, I showed you the little characters that I bought at the model store in Japan. And here's a microscope picture of the smallest characters, where you see that the features are so small that it was very difficult for the manufacturer to eliminate flash from the parts. And I could argue that this part could have been made better with higher quality, but given the small size of the mold cavities, I mean, gee, they're a millimeter wide or so, and the intricate features, it was probably pretty hard to get the plastic into those small cavities and eliminate flash. So that's what the part ended up looking like. Here's another example. This is what Protomold calls their design cube. Protomold is the same company that made the plastic injection mold model that we saw a few minutes ago. And they distribute this design cube to explain the features that can and can't be made by injection molding, and to help teach the relationship between process parameters and part quality. And you can go on their website and find more about it, and you can probably request one of your own if you're interested in taking a look. So this is, of course, an injection molded part, and the first thing we notice is that it unfolds from a cube to a flat orientation, and we can imagine to make the process as simple as possible, they probably use a simple two-part mold. And with that two-part mold, the halves move like my hands are moving, and the molds have a lot of interesting and intricate features that will help us understand more about defects in the process window. So in terms of the questions I listed, we know the molding orientation, it's like so. And now let's take the part under the camera and learn more about its features. So the first thing we notice by taking the cube from flat to folded is that they can build in living hinges, points of flexibility that you've surely seen in injection molded parts before. And they also build in a lot of snap fits. And design of snap fits is more of an advanced topic, but it's something you can find a lot of information about online. And the tolerances of different injection molded areas can be managed to be able to allow plastic to snap together. And that's one good thing about the compliance of plastic, is it can be designed to have nice snap fits. All right, so let's look at a few of the features on this part. So this face is really interesting because it has features of different thickness that are both vertical and horizontal, and these are dimensioned relative to the nominal thickness of the cube faces. So over here you have two features that if I took a cross section along the path of my finger are half of the face thickness and 1/4 or 25% of the face thickness. And you see on the thinner one there's a void, and this void is exactly a short shot that we just learned about. It means that as the plastic flows through the unfolded cube, the pressure is not high enough, or the flowability of the plastic is not high enough to completely fill this thin area. Another thing on this face is you have two features that are seemingly the same from one side, but if I open the cube, and look at the back side, one of them is cored out and one of them is not cored out. And knowing about cooling time and how cooling time is extremely sensitive to thickness, you can imagine that if possible you want to make your part uniformly thick so it cools at the same rate, and also to minimize the amount of stress and deformation. We can't get through all the features in the time we have, but on this face there are some more complex features that represent, for example, side action, buried features where you need a third direction of action to be able to mold the part. There are also examples for different kinds of bosses, raised features, and how you can mechanically support them using thin walls so you don't create features that are too thick. And then on some of the other faces we see different surface finishes. And we know that by finishing the mold surface we can affect a finish onto the injection molded part surface. So you have shiny faces all the way down to intentionally roughened faces and faces whose surface matches the machine surface of the tool. And I think through the reflections you can see the evidence of milling machining on this face. So now let's focus back on the face with the different thickness areas and jump to a simulation of molding of this face. And I didn't simulate molding of the whole cube, rather I imagined we were just making one face, and I built a CAD model and a simulation assuming that we were injecting the plastic at the center of the face. Right, like so. So let's see what the simulation looks like. This is once again from SolidWorks Plastics, and if we can start the video, you'll see the plastic flow beginning at the middle and flowing outward as we would expect. But we're just looping the simulation here, and you're seeing the dynamics of the flow are related to the local thickness of the part. And namely, the last location on the part to be filled is the place, the 25% thickness area where we saw the void. So I haven't adjusted the simulation conditions to capture the short shot, but it's exactly as we would expect. The thinnest part in the mold is the most difficult to fill. Also, you see that the thick feature that's not cored out takes a while to fill because you imagine the plastic has to accumulate all the way through its thickness. And likewise, these vertical fins, the ones farther away from the center, fill more slowly, and also the filling rate vertically of the thinnest ones is a lot slower than the thicker ones. And you can imagine everywhere on this cube, the flow is going to be coupled to the part geometry. And this is why simulation in injection molding is an essential tool to be able to get high-quality parts and design accurate tooling very quickly. I have some other simulation results. This is a simulation of the cooling time. It's just a static image, but the colors here represent the distribution of cooling times in the part. What I mean there is how long it takes each area of the part to reach a specific target temperature, and the obvious evidence is that the thicker part, the one that's not cored out, takes so much longer to cool than the rest of the part, an order of magnitude greater cooling time or more, a factor of 300 to 1. Next, here's shrinkage, and shrinkage is hard to see at this scale, but you can see there's a very light frame around the edge of the part, and the colored area is a little bit smaller. And by dimensional range, the maximum shrinkage is where we would expect it to be at the corners, and it's 0.45 millimeters in this simulation. And the size of the part is roughly 50 millimeters, so that's shrinkage of about 1%. What I said is the amount of shrinkage that we can expect for a typical thermoplastic. So it makes sense, but we also see that the shrinkage is distributed in its magnitude across the surface and throughout the different features, and that's important to recognize. And there's also warpage. Now I've exaggerated the warp deformation of the part, and all I want to say here is that because of the coupling between shrinkage of the plastic and the part geometry and how it's constrained in the mold, the part warps as it cools, and that deformation is something important to consider as well. If we look at other areas of the part, you can come back later and study these images, which we took with microscopes. For example, there are areas of the part that have a corner radius of 0.2 millimeters, quite fine radius, which would need a fairly fine tool. 0.2 millimeters is 200 microns. You also see that the hinges, the living hinges, come down to a thickness of about 1/4 of a millimeter. and in the rounded areas, the fillets of the tooling and the holes in this face of the part, you can get a sense of the relative radius in that far corner, about 1 millimeter, and also you see some blistering on the plastic, which is deformation of that edge as the part was ejected from the mold. Another thing we notice on some of the cube's features is what's called a draft angle. Now, draft angle is when we slightly slope the surfaces of some of our features to enable easier ejection from the mold. And here's what that looks like. Imagine we're molding a sloped, thin-walled feature like so. We would define the draft angle, let's call it theta, as the deviation between the surface and the vertical. And you can imagine that having this slope enables easier ejection from the mold surfaces, especially on the inside when we know that polymers shrink as they cool. And if we look at the cube from the side, we see that the fins have a draft angle of a few degrees. We measured the angle this way just to emphasize the deviation from the vertical. And even Lego bricks have draft angles, except the draft angle is very slight, maybe 1 degree. If you look closely, the surfaces look almost perpendicular. And there's no hard and fast rule for draft angles because the angle is going to depend on the thickness of your feature, the surface texture of your part, and other characteristics of the process. And here we see some pictures taken with a microscope of the different surface finishes on the cube. The labels here correspond to the labels molded onto different faces of the cube. And this is the as-machined surface, and you can see it's quite rough relative to the 200 micron or 0.2 millimeters scale bar. And at the bottom right is the smoothest, shiniest surface, and you can see a big difference relative to the rougher as-machined surface. So to conclude this section, let's say that the process window for injection molding is extremely important. We want to know the temperature and pressure that are needed to make a good part, and we want to be on the lookout for defects that might influence the part's quality. However, we also want to know that it's not good enough to be in the process window because the complexity of parts, different size features, different thicknesses, curvature, straight edges, corners, so on, means that the quality of the part and the presence or absence of defects is intimately tied to the relationship between the process parameters and the flow of plastic and its solidification. So to enhance your knowledge, you can certainly read more about common defects in injection molding, see more examples, and look up design guidelines for maximizing